Continuing with to the next discussion on Cantor set. We have seen Cantor set is countable and it's measurable and its measure is 0. Okay, moving forward. So in the construction of Cantor set, that is in constructing C1 we removed an open interval. While constructing C2 we removed 2 open intervals. In constructing 3 we removed 3 open intervals, not 3. We removed when from C1 to get C1 we removed 1 open interval. To get C2 we removed 2 open interval, 2 open interval. So to get C3 we divided 2 plus 2, 4 open interval, 4 open interval. Okay, now now from using these open intervals for each k, let OK be, wait a second, OK be the union of 2 power k minus 1 intervals which have been removed during the first k stages of the Cantor deletion process. That is O1 means is this interval, O2 means this interval union this interval union this interval. That's two open intervals removed in the construction of C1 and C2. And O3 is nothing but open intervals removed in the construction of C1, C2 and C3. So on OK is the open set or the set which is been obtained by taking the union of open intervals which is removed from the construction of C1 to Ck. So we get 2 to the power k minus 1 intervals. So thus our Ck is nothing but closed interval 0, 1 minus OK. You can observe this. Now defining O is nothing but union of this OK, k ranges from 1 to infinity. Then now OK is a union of open intervals, hence an open set. So this O is an open set. Now we see that C is nothing but intersection Ck, k ranges from 1 to infinity. Now this is nothing but intersection. Now Ck is nothing but closed interval 0, 1 minus OK, k ranges from 1 to infinity. Now using the set theoretic property, we get this is nothing but closed interval 0, 1 minus intersection OK becomes union OK, and that is nothing but O. So we have the Cantor set C is equal to closed interval 0, 1 minus O. Now we define a new function. Define a function say phi on O and O by we define a function phi on this capital O by phi on we define a function phi on O by say for a fixed k, since this O is nothing but union of OK, for a fixed k we take phi is a constant on OK for each k. So for a fixed k, phi is constant on OK, hence phi is an constant function on OK for each k, In particularly, since OK is the union of, it's a union of 2 to the power k minus 1, 2 to the power, sorry, yes, see, small correction. This OK is a union of 2 to the power k minus 1 intervals. Hence, we are defining this phi on OK. It takes 2 to the power k values. That means in each of the interval, this phi takes a constant value. This phi takes a constant value. Like see, in phi 1 sorry, in o1 is nothing but it's an interval, it's just an interval, that is 1 by 3 comma 2 by 3. So in this phi of x is equal to, say, we're taking a constant, and particularly we are taking, this is nothing but 1 by 2 in this interval. Now in O2 is nothing but it's a union of two intervals, that is 1 by 9, 1 by 9 comma 2 by 9 union 7 by 9 comma 8 by 9. Yes, okay. Now we are defining xi on O2 by, it's take one constant value in this interval and another one value in this interval. So it's a constant on this interval as well as this interval. Okay, now say we are taking it as, we are taking the xi of x is equal to, we are taking it as some 2 by 4 on 1 by 9 comma 2 by 9, sorry, 1 by 4 on 1 by 9 comma 2 by 9, and xi of x is equal to 3 by 4, sorry, it's 3 by 4 on 7 by 9 comma 8 by 9. Actually we are using this method, that is since my OK here O2 is not only these two interval, including this interval, so it is 1 by 3 comma 2 by 3, but in 1 by 3, 2 by 3, it takes the value 1 by 2. So in OK, now observe this, in 1 by 3, 2 by 3, it takes the value 1 by 2, 7 by 9, 1 by 9 is 2 by 9, it takes the value 1 by 4, and 7 by 9, 8 by 9, it takes the value 3 by 4, 1 by, yes, okay. Now this 1 by 4, 1 by 2 can also be written as 2 by 4, Now if you observe this, this is 1 by 4, 2 by 4, and this is 3 by 4. So we define, since OK is the 2 to the power k minus 1 intervals, xi, what phi takes 2 to the power k minus 1 values in OK. Okay, so repeating, see, after the construction of C in terms of O, we defining a function phi. On O by for each fixed k. Now we define phi on OK as follows. See, since phi is OK is the 2 to the power k minus 1 intervals. That's OK is a union of 2 to the power k minus 1 intervals. We defining phi in such a way that it takes a single value on each of the intervals. That is, in O1, since O1 is one interval, it takes one value. Now in O2 is the union of three intervals. It takes exactly one value in each of the interval. Now if observing this pattern, that is 1 by 4, 2 by 4, and 3 by 4, we define the phi on OK as follows. Since phi k since OK is the union of 2 to the power k minus 1 interval, phi takes 2 to the power k minus 1 values in OK, and the values are nothing but it is 1 by 2 to the power k minus 2 by 2 to the power k, comma 3 by 2 to the power k, and so on up to 2 to the power k minus 1 divided by 2 to the power k. It takes 2 to the power k values. It takes 2 to the power k values. Thus, for example, this xi of x, it will be 1 by 4 if x belongs to 1 by 9, comma 2 by 9, and it will be 2 by 4 if x belongs to 3 by 9, comma 6 by 9. And what is this? This is nothing but 1 by 3, comma 2 by 3. You can observe this. And next one is 3 by 4 if x belongs to 7 by 9, comma 8 by 9, as follows. We defined this with respect to O3. Now, so we extend. We defined phi on OK. So we take it in union OK. For each k we can define, so union k OK, that is nothing but O. So we now defined phi not, it is phi. So we defined phi on O is nothing but union of OK, k ranges from 1 to infinity. We now extend this phi to the closed interval 0 comma by phi of 0 is equal to 0 and phi of x is equal to supremum of phi of t wherever t belongs to O intersection closed interval 0 comma x, closed interval 0 comma of half open interval 0 comma x. This is when x not equal to 0. So when x equal to 0, we define phi of 0 is equal to 0. When x not equal to 0, we define phi of x is equal to supremum of phi of t, where t belongs to O intersection half closed interval 0 comma x. Now see this clearly this phi is it is 1 by 4, it is 2 by 4, it is 3 by 4. So if you observe my function, the phi is increasing each of the interval. So moreover, this phi is increasing on O. Its extension, now if you observe this is also used extended to closed interval 0 comma 1 using again O. So it's increasing not only on O, it's also increasing on closed interval 0 comma 1. Now for each point x belongs to O, x is in open interval on which phi is constant. So you see let x belongs to O, then x will be in one of the open intervals. Say x is in an interval. Now in this interval my phi is constant. So phi is continuous on x, continuous at this x. So we can say that phi is continuous on all of O on every point of O. Now let's take an x not in O, so we can say it's in C, because we have C is equal to closed interval 0 comma 1 minus O. So since x is not in O means it's in C. Okay, now let x belongs to C with x is not equal to 0 comma 1. Since the point this x belongs to C, it is not the member of, since it is in C, it is not the member of 2 power k minus 1 intervals in the first k stage. That's in OK, particularly in OK. This x does not belongs to OK particularly. That's it. It's not in the 2 to the power k intervals in the first k stages. whose union is okay. Okay, now if K is sufficiently large, if the K is sufficiently large, now see, I don't know how this say X is in, say, at some point we are getting some union of closed interval, say X is in some this interval. So we can observe that in some extent, in for larger K, we get two intervals. We get two intervals such that uh, this point X, this point X is lies between the two consecutive intervals of OK. Between, for large K, this X will be lies between, or between two consecutive intervals in OK. Now in this interval, choose the end point of this interval, say AK, and the first point of this interval, say BK, such that my X is greater than AK and less than BK. Now, what is phi of BK? Phi of BK minus phi of, sorry, phi of BK minus phi of AK. Now observe, phi takes constant value on this interval and this interval, and what is that constant value? Say the constant values changes in this direction: 1 by 2k, 2 by 2k, 3 by 2k. So difference of these two will be equal to 1 by 2 power k, because if it is takes 1 by 2k here and 2 by take 2k here, then the difference will be 1 by 2k. Okay, now so phi is increasing. Okay, since k is arbitrarily large, my phi, see, phi is increasing function, it's an increasing function. So in this point X, if it has discontinuity, at this point X, then jump discontinuity is the only possible type of discontinuity for an increasing function. For an increasing function, a jump discontinuity is the only possibility of discontinuity. But since as k tends to infinity, this tends to 0. This tends to 0. Therefore, my files to have a jump discontinuity. Okay. Now, so x naught. So therefore my function my function phi is continuous at this point X. In particular, it's continuous on every point of C. If it is also end point, similarly the argument we can say that in the similar argument we can say that phi is continuous at the end point 0 and 1. Now phi is constant in each of the interval of OK, in OK. Therefore derivative of phi on each of this interval in OK, it is 0. Moreover, derivative of phi in OK is 0. Moreover, derivative of phi in O is 0. Because phi being a constant function in each of the interval, and each of the interval contained in O, therefore phi dash is 0. Phi dash is 0 in O. Moreover, closed interval 0, 1 is nothing but C union O. Now measure of closed interval 0, 1 is 1, and measure of Cantor set is 0. Therefore, measure of O must be equal to 1. Thus we got a function phi which is increasing, continuous, and increasing, continuous, and it derivative exists and it is equal to 0 on a set of measure 0. Such function is called as Cantor-Lebesgue function. Cantor-Lebesgue function. Now this function is a Cantor-Lebesgue function, an increasing continuous on defined on closed interval 0, 1, which derivative exists and it is 0 on a set of measure 1 is called a Cantor-Lebesgue function. Now this phi is a Cantor-Lebesgue function. This is a Cantor-Lebesgue function. Okay, moving forward. Okay. Now we are going to define one more function, that is xi on closed interval 0, 1. Okay, moreover in this phi of 0 is equal to 0 and phi of 1 is equal to 1, and since phi is an increasing continuous function, my phi of closed interval 0, 1 is equal to closed interval 0, 1. That is, the phi map 0, 1 to 0, 1 using intermediate value theorem. Okay, we need this. Okay, now xi, we define one more function xi by on closed interval 0, 1 by xi of x is equal to phi of x plus x. We define xi on closed interval 0, 1 by xi of x is equal to phi of x plus x. Now clearly, since phi is increasing and x is strictly increasing, xi is strictly increasing. It's a strictly increasing function. It is strictly increasing, and this phi is continuous, x is continuous, so it is also continuous function. Also, since phi is continuous, strictly increasing function, it maps closed interval 0, 1 into closed interval 0, 2. Closed interval 0, 2. Now, the function phi is also we know that closed interval 0, 1 is equal to C union 0. C is nothing but Cantor set. Therefore, if I take phi of xi of closed interval 0, 1, this is nothing but closed interval 0, 2, and this is nothing but xi of C union xi of O. Xi of C union xi of O. Now, a strictly increasing continuous function defined on an interval as a continuous inverse. Therefore, now this phi xi is a function from closed interval 0, 1 to closed interval 0, 2. Now it is strictly increasing continuous. The result is, if I have a strictly increasing continuous function on an interval, then its inverse, that is xi inverse from closed interval 0, 2 to 0, 1 is also continuous. Now observe, C is a closed set in closed interval 0, 1. Yes, and this xi is inverse is continuous. So inverse image of a continuous image for a given a continuous function, inverse image of a closed set is closed, and inverse image of a measurable set is also measurable. Now we need inverse image of this function, that is phi xi inverse of C. This is nothing but xi of C. Since C is closed set, its inverse in this set is also closed, that is it is closed. It is closed in closed interval 0, 2. Similarly, okay, we need open set. Okay, sorry, I think I measurable set we need in terms of. Now again, O is an open set in closed interval 0, 1. So its inverse image, that is xi inverse of O, that is nothing but xi of O is open in closed interval 0, 1. So they both are closed and open. Closed and open set, open set, closed set, and open set in closed intervals 0, 1, and hence they are measurable, measurable. Now let now we seen that O is nothing but union of OK. K ranges from 1 to infinity. That is okay. O is nothing but union of OK is nothing but union of open intervals. Now we are rewriting this as O is equal to union I K. K ranges from 1 to infinity. Where what is IK? IK is the enumeration of collection of intervals that are removed in the Cantor removal process. That is, each open interval removed in the Cantor process, we take the collect a union of those intervals, and that interval will be that set will be equal to O. Now this K is not same as this K, so don't confuse. This is a different notation and this one is a different notation. Here it is an open set, here it is an open interval. Okay, now now my xi is constant on each ik. Therefore my xi is nothing but 5 plus x. Xi maps ik in onto a translated copy of itself, of length, of same length, of length. See, my xi takes phi of k to a constant. Since each is constant, this phi is constant, this phi is constant, but since we are adding x, we are getting a translated copy. We are getting a translated copy. Of ik of same length, so this xi is one to one collection. So since xi is 1 to 1, this xi is 1 to 1, we get a collection xi of ik where k ranges from 1 to infinity. This is disjoint collection. Since this is a disjoint collection by the construction of Cantor set, this is also a disjoint collection. Now consider m of xi of O, m of xi of my cap O. Now this is equal to m of xi of now union ik. K ranges from 1 to infinity. Now this is equal to m of union of this is xi of ik, where k ranges from 1 to infinity. Now this is equal to using the properties of measure. This is equal to now it's a disjoint union, so it is summation equal to summation m of xi of ik. Again, k ranges from 1 to infinity. Now m of xi of ik has it's an interval of same length as of ik, so this is nothing but summation k ranges from 1 to infinity m of ik, and m of ik is nothing but length of ik. Now this is nothing but measure of O. So we started with measure of xi of O, we get measure of O. Now since measure of C is equal to 0 and closed interval 0, 1 is equal to C unions O, measure of O must be equal to 1. So m of xi of O is equal to 1, because see, m of O is same as m of xi of O. This is equal to 1 implies m of xi of O is equal to 1. Now observe, xi is a function from closed interval 0, 1 to closed interval 0, 2 where we got an asset, we got a subset we got maps see this implies xi, yeah, okay. Also we have seen somewhere closed interval. Yes, yes, closed interval 0 comma 2 is equal to xi of c plus the union xi of o. So closed interval 0 comma 2 is nothing but xi of c union o xi of o. Now measure of measure of this is 2, and measure of this implies measure of xi of o is 1. Therefore measure of this implies measure of xi of c is equal to 1. Thus c is a Cantor set. C is a Cantor set such that my Cantor-Lebesgue function xi of c has measure 1. Thus my Cantor-Lebesgue function xi maps the Cantor set onto a measurable set. Now xi of c is measurable that we have seen. It's closed set, hence it is measurable. So xi of c is a xi maps Cantor set onto a measurable set of positive measure Now by now xi of c measure of xi of c is equal to 1. So that is the measure of xi of c is a positive. That's a xi of c as positive measure using Vitali theorem. If a set has a measure, a positive measure, then it contains a non-measurable set. That is xi of c. There exists a w contained in xi of c such that w is non-measurable. Xi of c contains a non-measurable set, say w. Now if you observe, my xi inverse of w is contained in c. And we have m star of c is equal to 0. That is measure of Cantor set is 0. This implies measure of xi inverse of w. Is equal to 0. Now xi inverse of w equal to 0. Since using the monotonicity property, this implies xi inverse of w is measurable. Now observe xi inverse of w is equal to w. That is, now observe, this xi is a Cantor-Lebesgue function which maps xi inverse of w is a measurable set. And w is a non-measurable set. Thus my xi maps a measurable set into a non-measurable set. My xi maps a measurable set into a non-measurable set. Repeating using Vitali theorem, we got a set which contained in w of c. Since w of c is a set with positive measure, it contains a set w which is non-measurable. Then thus we get the Lebesgue Cantor-Lebesgue function maps a measurable set into a non-measurable set. So why we need this? This is because okay, now go with this. We are interested in finding the answer for the question: if a set is measurable, is that set must be Borel set. Okay, now the answer to this question is no. Is no, because given a set closed interval 0 comma 1, given a set, there exists a subset of closed interval 0 comma 1 such that a is non-measurable. A is a set. This we have just seen. So there exists by Vitali covering lemma, particularly Vitali covering lemma. But using this observation, we've seen that there exists a set W here. That's a subset of C. Moreover, it's a subset of closed interval a comma b. So there exists a set A contained in closed interval a comma 1 such that A is non-measurable, but the Cantor-Lebesgue function image, that is xi of A, is non-measure sorry uh, wait wait. So there exists a set. mm, yeah, measurable set. So there exists a set A is measurable. See, xi inverse of w is a subset of C and hence a subset of closed interval 0 comma 1. So there exists a subset A of closed interval a comma b which is measurable, but xi of that set is non-measurable. Non-measurable. So this implies A is not Borel, that A is not Borel set, not a Borel set. Why? Why? Suppose A is Borel set. Suppose A is Borel set. Suppose A is Borel set. Now, xi of A is also Borel set. This is because using the result that since my xi is a Cantor-Lebesgue function is strictly increasing continuous function defined on an interval. So this strictly increasing continuous function defined on an interval maps a Borel set into a Borel set. So if A is Borel, then xi of A is also Borel set. Now if A is measurable, Borel sets are measurable, therefore xi of A is also measurable. But here we got that A is a measurable set, but xi of A is a non-measurable set. Therefore A cannot be a Borel set. If A is a Borel set, then xi of A is Borel set. It is not possible. So it's possible. Thus we got, if a set is measurable, then it need not be a Borel set. Hence the result. Thank you.